Oh, sure, that's fine. Sure. All right. All right, testing, testing. Does this work? All right, so we get started. It's 1 minute past Berkeley time. So I am Stuart. I'm the TA for the class. So Dr. Atwood is out of town for this lecture, so that's why I'm giving it. But he's going to give pretty much the rest of the lectures, as far as I'm aware. So yeah, so this is just a one-time thing, more or less. And this class, okay, so X-ray interaction with matter. Well, I guess the class is called X-rays and EUV radiation, but the first two lectures are going to be kind of an overview of the course and talking generally about X-ray interaction with matter to kind of get you oriented for most of the material in the course. And there's probably a lot of different backgrounds here, so it's okay if you don't know, there's no prerequisites, right? If you don't know certain things, that's okay. And I guess before we get started, maybe we can go around and everyone just say your name and your department and one topic you're interested in this course. We could start in the back up there. Great. Okay. What was that? The last thing? HHG? Okay. Luke? You can go to this row, I guess.
No, I'm from I'm not sure that I'm interested in that.
Okay.
I'm Yuan-Chun, second year PhD in chemistry, and I think I'm generally interested in X-ray.
I'm Paul. I'm a grad student in material science, and I'm just generally interested in the lab.
That's good.
I'm Kayla. I'm a grad student in physics, and I'm also interested in experimental physics.
I'm Conrad, also a graduate student in physics. Our group mostly has proto mission, so it's a back to all that stuff.
Me?
Yeah.
Oh, hi. My name is Leona. I'm an ASMT grad student. Interested in FDLs and plasmas, many other things.
I'm Jenna. I'm a grad student in chemistry. I'm interested in synchrotron X-rays and X-ray spectroscopy.
I'm Steve. I'm a grad student in MSc. I do TEM stuff, so we find out what all this photon stuff is about.
I'm Sarah. I'm an MSc, just interested in X-rays in general.
I'm Gautam. I'm in EECS, and I'm interested in soft X-rays.
I'm Margaret. I'm an ASMT, and I'm interested in HHG and synchrotron radiation.
Hi, I'm Tyler. I'm a grad student in the nuclear engineering department. I'm primarily interested in X-ray precision.
I'm Hani. I'm a fifth year PhD in physics. I'm just interested in this class.
I'm Sean. I'm a senior in engineering physics, and I'm interested in synchrotron radiation.
I'm Devon from engineering physics department. I'm primarily interested in X-ray applications.
I'm Chai. I'm in the nuclear engineering department, and I'm also interested in synchrotron radiation.
I'm Dan, third year in material science, interested in the X-rays in general. I normally do electron stuff, so X-rays are cool as well.
I'm nuclear engineering, and I'm interested in X-ray substances.
Jason, grad student E, mostly interested in synchrotron radiation.
Okay, great. So good. Looks like everybody's here for good reasons. So, so this class, it's about the short end of the electromagnetic spectrum: EUV, soft X-rays, hard X-rays, tender X-rays, which aren't on this chart. Somewhere in between hard and soft, although tender is not really between hard and soft. So basically, this electromagnetic spectrum. It's a wavelength on the top, energy on the bottom, and they're always going to be related by these universal constants. Is my mouse there? Okay, that's fine. And we can do many, many applications. So seeing through visible objects with hard X-rays, or elemental and chemical specificity by being able to distinguish the different absorption edges of different elements, being able to see smaller objects, which the absolute resolution you can attain with light depends on the wavelength, or with any wave. So going to smaller wavelengths, we can get better resolution down to a point. The best resolution is actually in the soft X-ray region, though, not hard X-rays, because while the wavelength is smaller, it becomes more and more difficult to fabricate the optics. So at a point, going down in wavelength no longer helps. But we can get down to, use 1 nanometer resolution or so with soft X-rays. And also writing smaller patterns. So this is something that I work on mainly in my research for extreme ultraviolet lithography. So this is an example of the projection optics in a lithography tool, where they are exposing an integrated circuit being manufactured. And so by the same token of the wavelength improving resolution, it also improves the resolution of a projected image as well as a recorded image. And this is kind of really the next big thing in continuing Moore's law. And one equation that's probably going to show up on many slides is this n equals 1 minus delta plus I beta, where delta and beta are both much less than 1. So this is something, n is the index of refraction here, and something that's characteristic of pretty much all materials in this high energy, for high energy light. They all pretty much interact weakly. So basically, you can think all atoms are basically the same, except they have a different amount of phase and a different amount of absorption. But it's always going to be a relatively weak interaction, which is different than, say, visible light, where we have something like glass, which has an index of 1.5, much more than 1. There are materials with index of like 4. So that sort of thing can only exist at larger wavelengths. And this is the course textbook. So you can get it at Cambridge or Amazon.com, and you can also, if you just want a PDF ebook version, you can also get that on the Berkeley Library website. So, if you want the hardcover version, then buy on one of these sites. And so X-rays, right? One thing is they can probe pretty much all the transitions in all the elements on the periodic table. Okay, photon energy. So basically the point this is that photon flux is just proportional to power. So if we know the wavelength or the energy of an individual photon, then just by measuring the power, we can count photons essentially. That's a key thing that's only possible because of the quantization of the energy. So there are a few types of basic processes that we're going to be interested in. So one is an electron collision ionization. So you have a primary electron that knocks out this core level electron, and there's a scattered primary which has lost some energy, and a secondary electron. You could also have photoionization, where instead of an electron hitting the atom, now there's a photon which provides the energy to ionize this atom and gives the remaining energy to the ejected electron. And then you could also have this kind of fluorescent emission, so where there is just a natural decay of an electron from a higher state to a lower state, which emits a photon of that amount of energy of the difference. And then you could have this a little bit more exotic, is an Auger process, where an electron relaxes to a lower state, and essentially because of some conformational reasons, then it becomes energetically favorable to kick out another electron. This is a little bit more, less common of a process. Yep. And, okay. So, right, the key is that if you look at this chart of the K edge and the L edge, so basically the furthest in electron states, which is the K edge, are the most tightly bound. So basically to ionize them, you need to have a photon with at least that amount of energy. So I think that the point of this table is that most of these, or a lot of these are in the X-ray or the soft X-ray regime. So to ionize these atoms, either from the K edge or the L edge, a lot of the time would require, X-rays or soft X-rays or EUV. And so this is, right, energy transitions. When an electron decays from one of these levels to another, it's going to emit a photon of this amount of energy, but not all the transitions are possible. So essentially the only transitions that, there's certain rules that, like, you've got to go, plus or minus 1 in L if you do 1, I don't know, there's all these rules. But basically the point is that there's a bunch of possible states, but not every combination of two states actually is an allowed transition. So when you look at the spectrum of one of these atoms, you're just going to see this reduced number of absorption edges. Okay, and there's a tape. There's all this information is available on the website. So CXRO, Center for X-ray Optics. And that's where I work with a group there. And there's a lot of really useful information on this website about the periodic table. And I'll talk about some other really useful data that's on this site. All right. So this is just showing there's these different states that, right, the 1s, 2s, and the p's. So they essentially the more tightly bound states have this smaller radius, and then these higher energy states are, tend to be further from the atom. And decay. So when you have something in one of these excited states, essentially it will oscillate between that state and the lower state. And over time, it will become overwhelmingly probable that it just ends up in the lower state, even if it starts out in the upper state. So this is showing some experiments you could do. So photoabsorption experiments, and basically you see a similar kind of trend in both And the top one is looking at, centimeters squared per gram, so more of a macro scale view of a continuous material with some density, right? And this is the absorption would decay exponentially with depth proportional to this constant mu, which is what's plotted, and the material's density. And the bottom plot shows a similar kind of trend, but instead this is for the number of atoms times the absorption cross-section. So, or the density of atoms times the absorption cross-section. So that's more of a microscopic view. You can see it as atoms with some spacing and some absorption cross-section, or you can see it as some material with a density and a certain, this mu factor. In either case, you see some of these absorption edges specific, particularly the one at around 1,000. Yeah. And this is a plot of the scattering factors for silicon. So this is the mu parameter, which is the absorption. And particularly, you can see two really clear absorption edges, so there's the L edge around 100 eV, and then the K edge around 2,000 eV. And so the point of this, or one really important thing for my research and for EUV research, is that 100 eV, so basically at energies slightly below the absorption edge, the absorption is very low. So that means if we work, and so what energy I would typically work with is about 84 eV. So that's right below 100, and basically in that region, silicon becomes a very non-absorbing material, so it becomes a very useful material for making optics. And talking about different types of X-ray optics and soft X-ray optics is a big part of this class. So there's like many different ways that light could interact with matter. So one would be kind of isotropic scattering from a point, something that is much smaller than a wavelength of light would send light in pretty much all directions. There's also non-isotropic scattering, which is something that is partially ordered. So it has some structure which is maybe close to the wavelength of light and sends light in many directions, but there is some structure to it. Diffraction. So for example, this is a crystal lattice where you'll see these Bragg peaks determined by the period of the lattice. That would be diffraction. Also, another type of diffraction would be diffraction from a well-defined geometric object. So like a small pinhole will create this airy disk pattern, which has this characteristic null at a certain angle. And also, refraction. So that's one probably most of you are familiar with, the angle that light going from a medium with one speed to a medium with another speed. If it's going at an angle, the angle will change. So one thing that's unique, though, in this region compared to visible wavelengths is that at visible wavelengths, you'll never have an index lower than 1. Essentially, the speed of in the material will always be slower than in a vacuum. But in these higher energy regimes, you can have an index less than 1. So actually, essentially, it means that the phase is evolving more slowly in the medium than it would in the vacuum. And basically, refraction will now go the opposite direction from what you would have expected in visible light. And also, because of this, so in visible optics, there's a concept of total internal reflection. Now, because the index of this material is less than 1, we can have total external reflection. Really, it's actually total internal reflection where the medium is the vacuum, right? And this is very important for X-ray mirrors. So we could have, so basically this is in the textbook, chapter 2 is about single scatterers, like an electron or an atom, and chapter 3 is about materials, so going up to the more macro scale view. And right in these chapters, it'll talk about how are scattering, refraction, and reflection related, and how do they differ for amorphous or crystalline materials and forward scattering. So all this arises from these Maxwell's equations, and these different arrows are supposed to show the different contributions of these various scientists. So Faraday, yeah, I didn't make these slides, so I don't know exactly which is which, but in the end, the real point is that you get a wave equation. So the electric field, essentially, so it's a wave equation on the left-hand side, and then the right-hand side is this current derivative term, and that is basically like a forcing term in the partial differential equation. So if you have no current, right, if the right-hand side is 0, then it's really just going to become, the solutions, homogeneous solutions, will be plane waves. So that's why basically light behaves like a wave. And so from Maxwell's equation, we get the wave equation, and then chapter 2 is about the wave equation in a vacuum. So we talk about single electron radiation, scattering cross sections, Thomson scattering, and eventually get to the atomic scattering factors. And then in chapter 3, it goes into the more macro scale view, and right down here talking about how we actually determine the index of refraction from scattering factors, and actually how we measure both real and imaginary parts using Kramer's Kronig relationship, which I'll talk a little bit about. So it's chapter 2. So every chapter has this kind of panel on the first page with some key equations. It's pretty useful to, if you've read it and you just want to flip back, like it's actually very useful having this page. And so scattering cross section. So basically what a scattering cross section is, right, is the ability to remove particles or photons from their path. So it could include both scattering and absorption would, well, I guess, increase the cross section, right? Or right. Well, I guess only the scattering part would be just the phase, right? So the scattering cross section is the power scattered divided by the incident Poynting vector, and so the units are area. So basically, you can think of a cross section as a cross sectional area, loosely speaking, and so there's a few cases, like for a free electron, it would have this scattering cross section, which is, basically the electron radius squared. So it's something like the area of a circle, or the cross sectional area of a sphere. Now for a bound electron, you have this additional energy dependent term or frequency. So this is basically because of the electron being a harmonic oscillator. And so now how close your photon energy is to the oscillation frequency will really affect how strongly that scatters, right? And this is closely related to these absorption edges that you see. So when you're right at that frequency, then it will scatter or absorb a lot more. And then multi-electron atoms, everything gets collapsed into this F factor, scattering factor, which are, they've been measured and tabulated for a bunch of elements and also compounds at Lawrence Berkeley Lab. And they're on the website. So that's a very useful feature of the website, actually, is that they have all the scattering factors for pretty much every atom. So here's an example of the scattering factors. So the left side is and it's for silicon. So the left F10 is the related to the phase, and F20 is related to absorption. And so looking at the F20, right, you see this edge that we saw before at 100 eV. And also you can see where there's these absorption edges, the phase term also has this very sharp behavior. And you can actually see that's actually why that term goes negative. So the negative, you see where F10 goes negative, and that is where the index of refraction is less than 1. So it's right, has to be right around an absorption edge, I believe. And so chapter 3, talking about wave propagation, refractive indices. So here's this same thing again, but so at the top, this is the equation for how you translate from scattering factors to index of refraction. And basically, there's just this scaling factor, which is the Na is the density of atoms times the electron radius times the wavelength squared over 2 pi. So basically, in this equation, and also, the F0, F1 and F2 are both functions of wavelength as well. So really in this equation, like everything pretty much is known because people have measured the F1 and F0, and assuming you know the wavelength, but the density is pretty hard to know in advance. But not impossible, obviously. So, and also on the CXRO website, they have some nice apps, like calculators for calculating index of refraction or reflection and transmission through thin films and things like that. So glancing incidence, we're going to talk about. So, Snell's law, and basically, right, we talked about total external reflection, which is going to happen when the angle of refraction goes to 90 degrees. Right, so essentially, if you go through and work it out, you'll get this. So basically, right. So if it was this Snell's law is for only non-absorbing materials. But now if we add absorption in, so the black line is what it would be with no absorption. And so then basically it's, if it's below this critical angle, you'll get 100% of the power reflected. But in fact, if there's absorption, it decreases that. So in reality, even if you're below the critical angle, you won't get total external reflection. So that is, right, depends on how absorbing the material is. So now talking about scattering. So this is showing us saying if we have a sinusoidal distribution of atomic density, these two wave vectors form an angle, and right, so this is working through the math. So we have an incident wave, some periodic thing with a certain wave vector of periodicity, and then some scattered wave. And basically, if you work through it, you get to Bragg's law. So, which is relating the angle of this scattering with the period and the wavelength. And so this Bragg's law, right? This is what we see in crystallography, where we have Bragg peaks. So, so yeah, that is saying that we have this crystal lattice. There are certain planes where we have a periodic, cross section, and then depending on the spacing, the d-spacing of that period, the smaller that period, the larger the angle of diffraction would be. And so this is at the atomic scale. And we can also do this at a more macro scale using a Bragg mirror. So this is a Bragg reflector, though this is a multi-layer mirror, which we use a lot in EUV lithography, EUV optics. So basically the idea of this is it's periodic stack of two materials. Here it's molybdenum and silicon. And they're spaced in such a way that all the reflections add up in phase at a particular angle and wavelength. So basically, this is a way to get around the kind of difficult, because basically a mirror, right, in optics, if you want to make it of something that is, something reflective is something that has, like metal, right? So it's like a very absorbing material. So when you have a weak contrast, like delta and beta, much less than 1, basically you can't get a good mirror, essentially. So, like a simple mirror. So we need to use these Bragg mirrors, which are based on interference. The downside of that, then, is that they only work for a specific wavelength and angle, right? So it's not quite like a, typical mirror. Okay, so we're going to talk about coherence now. So temporal coherence. So this is saying if we have some wave packet with some wavelength, average wavelength, and a spread of wavelengths. So every one wavelength, there's this deviation of delta lambda. And the point is that if it travels one coherence length, then there'd be a 180-degree phase shift. So essentially, the wave packet now is no longer all in phase. So you'll stop seeing fringes or interference. Spatial coherence is slightly different, so and usually a little bit harder to grasp than temporal coherence. So spatial coherence is about if you separate two points in basically space and or angle, how far can you separate them and still have them interfere with each other? So this is like the double slit experiment, and on the right-hand side is showing like a point and then a second point. So if this point, grows to be large enough, it won't be coherent anymore, and you'll see less and less contrast in these interference fringes. Or another way is if you have these 2 points, if you move them far enough apart, they're not going to create high contrast fringes anymore. So this is a way to look at it that spatial coherence is basically the transverse direction of the wave, and temporal coherence is basically the longitudinal direction of the wave. They both have to do with a spread. So you could actually think of both of them as really the same thing. They're both about a spread of wave vectors. It's just temporal coherence is about a spread of wave vectors in the longitudinal direction, and spatial coherence is about the transverse wave vectors. So formally, the way we define coherence is it's about an average correlation between 2 points in space. So the points 1 and 2, and then we take their average correlation, normalized. If it's 0, there's no correlation on average, so that's incoherent. If it's 1, they're perfectly correlated, so that's coherent. And if it's somewhere in the middle, that's what we call partially coherent, which is where really everything physically is. But so yeah, we can, but it behaves quite differently, and I'll talk a little bit about that if we get there. So this is an analogy in the book that you can think of coherence as like a marching band. So they're all totally coherent if they're all marching at exactly in sync, or I guess exactly correlated with each other. And maybe you could imagine that as they walk forward, they sort of get out of phase with the frequency they initially started with. So that would be like temporal coherence. Or it could be that as you go from one person further away, these people are getting out of phase. That would be like spatial coherence. So this is a kind of famous figure showing the concept of coherent and incoherent light. So on the top we have a light bulb, which is not temporally coherent or spatially coherent. If you put a pinhole, then you can make the light be spatially coherent at a long enough distance. So you can see, like, at the right edge or the left edge, there, the waves are almost perfectly vertical, which is like a coherent plane wave. Now you can also make it temporally coherent by adding a color filter. And so if you use a color filter and a pinhole, you can make incoherent light into coherent light. On the other hand, the bottom is representing a laser, where it creates temporally and spatially coherent light without filtering. Although there's some kind of filter inside of the laser itself. And so spatial coherence, right, this is saying, one thing is, right, so for the spatial coherence, if we have 2 points that are moving further apart, and these are the conditions in red for full coherence, essentially. So yeah, these are, okay. So the lower equation is pretty easy to interpret. So the coherence length is this number, which is, it's basically the number of periods that it takes to go out of phase times the wavelength. The top one is a little less easy to interpret. So basically the d dot theta equals lambda over 2. The idea is that if d dot theta is greater than lambda over 2, then it's not fully coherent. It's kind of a misleading equation because they're not always equal, right? It's not saying they're always going to be equal. Right, and then there's a big difference between uncorrelated and correlated emitters. So if we have uncorrelated emitters here, they can still be spatially and temporally coherent with each other. So you can see interference fringes, but it's self-interference. So the electric field over time, if you just look at this one point, it's kind of varying randomly, but as a time average, they can still form interference fringes. But if you have correlated emitters, then you will see actually in time the electric field at a certain point is actually going to be periodic in time. And so this, basically the thing is with correlated emitters, you can get basically, instead of with uncorrelated emitters, the power is going to scale with the number of emitters, but with correlated emitters, it's going to scale with the square of the number of emitters. because now the electric fields add together in phase, and then you square it. So this is close, I think, to where I'm going to stop. But so these different types of sources we're going to talk about in the class. So one is undulators, which is a synchrotron, really. Basically, so free electron laser. I'm going to only talk about a little bit about synchrotrons, and then I think that's as far as Dave asked me to go. High harmonic lasers and plasma EUV atomic lasers. So synchrotrons, like at the advanced light source, basically what the key to how they work is that when you accelerate electrons to relativistic speeds, the period of the undulators from the frame of the electron undergoes a length contraction. So the wavelength of these magnets now can become basically arbitrarily small if you could accelerate the electron fast enough. And so this is showing what's happening. And the other thing is that it's an angular dependence, though. So like you see on the right or the left, only the forward scatter or the forward propagating part has this very, very small wavelength. And as you go to other angles, the wavelength will get much longer. So basically that means that only this narrow part of the cone will actually have the high energy light that you're really trying to get from a synchrotron. So this is representing this cone. And basically, right, we have this undulator with a period lambda u, but in the frame of the electron, now we get the wavelength like with this factor of gamma squared. And so there's a central angle, which is kind of telling you about the spatial coherence of the light. And that is going as like 1 over gamma root n. So basically, if you increase the number of periods in your undulator, you'll get more spatial coherence. And then the bottom, the temporal coherence also is going to increase. So the more periods you could have in the undulator will give you more coherent light in the central cone. And so this is showing a little bit, showing about how you can achieve more coherence. So this light is already somewhat coherent, but if you want, you can further increase the coherence with like a pinhole and so a spatial filter, which is a pinhole and an aperture. And right, so this d and theta, the idea with the d and theta and then lambda over 2 pi is that if you want full coherence, then you design your d and theta so that you meet this condition. That's really what it means. And okay. And this is, I think, the last slide I'm going to show. So this is showing just what we can get at the ALS. So the top left one is showing all the power in the central cone versus energy. So the n equals 1 and n equals 3 are first and third harmonic. So there's going to be this third harmonic, which has 3 times the energy, but lower amplitude. But if you want to go to higher and higher energies, you can get about 3 times higher by using the third harmonic. So in the central cone, there's like a few watts of power at max, and then in the bottom left is talking about if we use a coherence, a temporal coherence of lambda over delta, lambda is 89, and then it goes down to the milliwatts. And then the last one is if we go down to 10 to the third temporal coherence, and then it's in the microwatts or hundreds of microwatts. So essentially, right, we can get, you can achieve basically any level of coherence if you're willing to throw away some of the power. Okay, and so that's all the slides. I have some like announcements, but are there any questions or comments on the topic so far? Is this stuff that most of you have seen? Like, raise your hand if you feel like you're pretty familiar with most of what I covered. Okay, so, and if you're not, okay. All right. So basically, okay, so I'm just going to do some announcements. So there's going to be like about 10 or 11 homework assignments, like one homework assignment per chapter, basically. And I think Dave said that you're going to be allowed to drop 2 of them. And they're not, so they're not like really long, really. And it's fine if you work in groups also, right? Just you have to turn in your own work at the end of the day. There's no final, but there is a final project, which is a write-up, like a few-page write-up and a 5-minute presentation about basically looking further into some of the one of the topics that we covered in the class. So it can be based just on it could be based on reading a couple papers, or it could be something related to your research. But it's just a short topic. Short. And so also the professor said to tell you that this is a graduate class, so it's graded on a curve, okay, from A- to A+. So he said, tell them that, but I can't tell them that. So there's no midterm, no. So it's just homeworks and the final project, yeah. And probably a small amount for participation. And there's also 3 lab tours. So we do a tour of the Advanced Light Source, the SCLS at Stanford, and one of the high harmonic labs in the chemistry department on campus. So that's also a really nice part of this class. And I'm also going to send out a survey of what topics everybody's more interested in the course, right? Because we don't necessarily need to cover all the chapters, or we can spend less time on certain chapters. And so that's just going to be a Google Forms. So if I'll just send it to the B-Space. So if you're registered to the class, you should get that. And all right, so yeah, that's it. Thanks.
Where can I find the homework link?
Oh.
Is there a
yeah,
course
yeah.
setup, or like?
There is a B-Space, I believe.
Yeah.
Are you so you're registered? Yeah. Let me just see. I'm pretty sure it's gonna be just on the B-Space. So.
If I go to B courses.